Course. Today we will study BGP, external routing in the internet. As this is showing, external routing in the internet is self-organized, contrary to what we have seen inside the domain, where we use RIP, for example, with a well-defined network model and shortest path routing algorithm. In the internet, things are a bit more fuzzy because there is no entity running the internet. Before we get there, a small scheduling issue. As announced in the first lecture, that we do a clicker test every second week, and the program of the clicker test is up to the previous week. So tomorrow we have clicker test number 5, the program of which is on the all lectures until last week, primarily on the last 2 lectures of last week and the week before. Some people don't like the idea of having a clicker test on Friday, December 19, although this is the last day of the semester, so we're all supposed to be working here, I guess because of flight schedules and other problems. We can do a test before. We can do it practically only the previous week because it's impossible to get both a room and a slot where all of you are guaranteed to be able to be present. So the only alternative is to move it by 1 week before, but there is no free lunch. If we move it by 1 week before, the program would be the same. So we will cover everything, including the lecture until Thursday here. So just so that you have all information at hand. We won't vote today. Think about it, discuss it. Tomorrow we'll vote on it, and the majority will take it. Yeah?
What is the due date for the last lab?
There is no lab in the last 2 weeks. Right. So the last lab is lab 6. Yes?
Why not do the clicker test during the lecture on the Thursday instead of Friday?
We don't have enough space to make it in good conditions here. That's okay, so discuss that on the forum everywhere, and we'll come to a decision tomorrow. Today we discuss external routing, inter-domain routing. We'll do it as usual in 2 parts. First, we'll discuss how it is designed, and second, we will see how in practice it works in BGP. And then we'll do a 3rd part in the lab starting next week, as usual. So what is the problem? The problem is of 2 natures. First, organizational, and second, scale. We have seen that with RIP, and we will see a bit later other methods, link state, we can design routing inside a network. But there is not one network in the internet. There is Swisscom, there is EPFL, there is Switch. All of those are run by different entities, and there is no body that controls all those networks. So we need a method for doing routing globally that does not require a team of system managers who agree on what the metric is, on which protocol they will use, etc. So we need something relatively simple that is accepted by everyone and works in a self-organized way. Self-organized means every entity, every network manager in the internet does their own thing, and the result is simply the emerging property of the cooperative or non-cooperative behavior of all the networks. So again, there is not a central computer or a set of servers in the internet that would run the internet. There's a few DNS servers that in some sense we could view as central servers in the internet, but for routing, there is no global entity. So the internet is split into what is called domains. A domain is something that is run by a company or by an organization. EPFL is one domain. Switch, which is the internet service provider for Swiss universities, is another domain. Swisscom is another domain, etc. Domain can be small, like EPFL, even though EPFL is big, but from a networking viewpoint, it's a small network. The network can be large, like Swisscom has a much larger network. AT&T, US Sprint have a much, much larger network, not to speak of Chinese operators. And then a bit of terminology. We say that a routing protocol is interior, that's what we've seen so far, if it is inside a domain. Otherwise, it's called exterior. Inside a domain, you do what you want. You use RIP, whatever version of RIP. You can invent your own protocol, and Cisco and Juniper have their own variants of their own routing protocols. The most widespread protocols are the one we have seen, RIP, OSPF, that we'll see a bit later, and IGRP or EIGRP, which is a variant of RIP with some flavors of OSPF. In contrast, for exterior interdomain routing protocol, there is only one. There is only one, and it's BGP4. Of course, as you can imagine, lots of people, like university people like us, have invented other protocols, IDRP, variants of BGP, etc. But in practice, there's only one. It's at its version 4. It has evolved a lot. In particular, now it supports IPv6 in various ways. But it is only one protocol. Why there is only one is by nature of the problem. If we want something that works with everyone, then it's very difficult to change. BGP is not optimal, as we will see. It has a number of heavy parts. But if you want to do something better, it's worse than moving from IPv4 to an IPv6. You really need to change in a synchronous way all protocols, all routing protocols everywhere. And in practice, nobody has dared do that today. A bit of terminology. A domain, from the viewpoint of BGP, is called an autonomous system, AS. And there is a small subtlety. Sometimes people use the word ARD, autonomous routing domain. The difference is only that an AS has a number and an ARD does not necessarily has one. So what is an AS number? An AS number is a 32-bit number that identifies the domain. For example, switch is 559. Renater, which is the French switch, is 2200, etc. So each domain number is used in the routing protocol, in path vector routing, as we will see in a minute. This is not an IP address. Although it's 32-bit, it's like an IPv4 address, but it is not an IP address. It's just a number of the domain. Some domains, like EPFL, have no number. EPFL is an autonomous routing domain. It's run by no one else than EPFL, but it doesn't have a number. The reason being that it is what is called a stub domain. It is a domain that is at the end of the hierarchy. EPFL connects to the rest of the world through switch. So all routing, anybody in the world that wants to connect to EPFL has to go through switch. So the rest of the world doesn't need to see that there is something called EPFL. The rest of the world needs to see switch only. So as IPv4 addresses, ARD numbers are a scarce resource. So if you want a number, you need a very strong reason. And we try to have as few numbers as possible. Here is a picture of how things can fit together. This is showing, so here we see the clouds less well, so let's look here. Here, this is showing a world with 4 clouds. Every cloud is a domain. For example, there could be a small domain like here where we run RIP and RIP-NG for IPv6. Then between the domains, we will run the BGP protocol. So a priori, we can think of the BGP protocol as something that is run between routers that are at the boundary of the domains. Here again, the self-organization idea means you don't put a router in the middle between 2 domains, but each of the domains has their own router, which may be of different manufacturer, different type of routers, and each of them talk together the same BGP protocol. Then you can see large domains that run a routing protocol for large domains that we will discuss a bit later. And here this is showing a stub domain like EPFL is, that is connected only to this transit operator and is not directly connected to the others. In this case here we run BGP, but in a case like this we could perhaps avoid running BGP if we're connected to only one domain, as we will see a bit later. The method of BGP is path vector, as we will see in a minute. And the main goal of BGP, contrary to what is done in RIP, for example, is to be able to implement policy routing. With policy routing, we mean that in the internet, we don't simply want the best path in the sense of the shortest or the lowest delay path or the high throughput, but we may have what is called policy reasons to forbid a path or to prefer another one. Policy reasons have to do with business. For example, if you are a transit operator, you might not want to carry the transit traffic for Swisscom, for example, if Swisscom doesn't pay anything to you, because they prefer to connect to US Sprint, for example. Then you will say, okay, then your traffic to all US citizens or US people in the US should go via US Sprint, not via me, because you pay nothing to me. So there might be good paths that are not used because of business reasons. This is called policy routing. We'll discuss that in detail in a few more moments and in the lab. So BGP uses path vector routing. So the problem here is, even if we do policy, we want a way to find paths that we like, that are good in some sense, or even the best path. But in the internet, it's hard to imagine that we would use shortest path routing like we do in a domain. Because for that, we would need to agree on a metric everywhere. So all links in the world would need to agree on the same metric. It would be possible, but instead of that, we take another approach. We say, okay, everybody can have their own definition of their metrics. We don't care. The only thing we do is we associate with every route the list of the complete path. And then we will decide which path we prefer, as we will see a bit later. So how does it work? Here, for example, I'm showing ASA, so this is, think of it as its AS number, that has two prefixes, N1 and N2. They can be IPv4 or IPv6. BGP works for both IPv4 and IPv6. Very often people run one process of BGP for IPv4 and IPv6 at the same time, but in some other cases, some people prefer to have one process for IPv4 and another one for IPv6. So in the lab, we'll do the former approach. Here, so those two prefixes are exported to the two neighbors. So A speaks to B and C, is connected to the world only through B and C. So BGP routers in A and C will talk together, and A will send to C a message saying, I am AS number A, and here are the two prefixes I have, N1 and N2. Then C, if C decides to repeat it, with policy routing, C might say, oh yes, but I don't want to have anything to do with your prefixes. But if it agrees, then it will pass it along to D, who will pass it along to E. So at the end, E will receive through this direction the information that there are the two prefixes, N1 and N2, plus the accumulated path, a bit like we do with source routing. So we accumulate not the detailed route, but simply the collection of the AS numbers. So E will know I know how to go to prefix N2, for example. All I need is using the path DCA, which means my next neighbor, I should send it to D. But via B, it will get another information. It will have another path, which is BA and N1 and N2. So E will have those two information and will have to pick the best. One way to pick the best is to use the shortest AS path. In that case, E would prefer this one. But perhaps E has something against B. E doesn't like B because E is a bad competitor of E, for example, and you don't want to send traffic to B, in which case you would prefer this one. Or it might be the other way around. E doesn't like C and wants to send a lot of traffic to C because C has a lot of money, and E is a small operator that's trying to save on the bandwidth of the links. So it might prefer to go this way by having the path information. So that is the first element of BGP. In BGP, all routes have the complete path, and then we can use it to do whatever we want on the paths. Of course, in practice, we don't usually do whatever we want. A very simple rule is usually to try to minimize the number of AS numbers in the path. If we compare to distance vector, what we have done in distance vector, we have added the distances. So when we pass a route to someone, we would say, I would have, if the distance would be counted in number of AS domains, I would have 3 here and 2. This is what we would do if we would apply the distance vector philosophy, which would be good enough if the only criterion is to choose the smallest AS path. But we don't do that because we want to keep the freedom to judge a route based on the identity of the ASs that we go through. That is the first reason. In practice, BGP is implemented in routers that run BGP. They are called BGP routers. Sometimes we find the terminology BGP speakers. As I mentioned, there is one at every edge of a border, like on the border between 2 countries, Slovenia and Croatia. You have a police check at each edge. So the same thing here will happen. We will see in OSPF there are other cases of big hierarchical routing where we do differently. But for BGP, every BGP router belongs to one domain. Then, of course, the domains that are at the boundary, like B and D, they speak to each other across the border. So they have to be connected. Although those guys are competitors, they have to be connected. Of course, if you want to provide internet service, if you're Swisscom, you have to be connected not just to Switzerland, right? Otherwise, it's not very exciting for customers. So you're connected to the neighbors, and the B and D speak together using BGP. Similarly, A and C, G and E, and F and H. But also, we need inside the domain to carry the information. So D has learned something of the outside world from B. But this information needs to be passed along into the domain. For that, the choice of BGP is to require that there is what is called a mesh. A mesh means all BGP routers inside the same domain are directly connected to each other over TCP connections. They are not directly connected in the sense they are not on link. For example, C and F are not physically connected to each other. To go from C to F, we need to go either via R or via E in 2 hops. However, there must be a direct BGP dialogue between C and F that goes over a TCP connection. So that's the first thing that is a bit special in BGP. So inside the domain, all routers talk directly to each other. That's very different from RIP, for example. In RIP, F learns everything about C, but indirectly. In RIP, F learns from C by comparing the information about C that is given to F by E, R, and D. In BGP, that is not the case. In BGP, C will directly speak to F, and D also, and E also. When they speak together, they use also the same protocol, BGP. So BGP is both a protocol used between domains, but also inside the domain between all BGP routers. And it's the same protocol, with 2 very minuscule differences that are given here. The first difference is that when D speaks to B, all the routes that D has learned, when D exports them to B, D will add the AS number of this domain, of D3 here, because we are moving to another domain. Of course, when D passes some information to F, you don't add an AS number to it. So that's an obvious, because we're in the same domain. So that's an obvious difference. A more fundamental and important difference is the above one. When F learns a route from a neighbor, now F can learn something from H or from E, for example. E is a neighbor in the same domain, H is not in the same domain. In a case like this, F is allowed to repeat the information learned from H to E, or to D, or to C, but is not allowed to repeat to D the information that it has learned from E. Right. So you are not allowed to repeat inside the domain information that you have learned inside the domain, which makes sense, because inside the domain we assume there is a mesh. So anything that E has learned, C has heard it directly from E, so there's no point repeating from F the thing that E has said to F, because C has the same information already. So it's consistent with the concept of a mesh. Question?
Inside the domain, internal BGP, does it imply a listing kind of?
No. So inside the, so yeah, thank you for your question. I forgot to mention something. So we will often find in written documents terms like IBGP and eBGP, external BGP and internal BGP. But be careful, this is a misnomer. There is only one BGP. The only difference between E and IBGP are those restrictions here. So what you're allowed to repeat. But otherwise, the protocol is exactly the same. In particular, it's path vector. It is not distance vector or link state. So it is not link state. There is no global topology of the internet in BGP. Yes?
Why don't you have only one BGP router for each? Why do you have like C, D, R, E, F? Why do you have these 5 routers? For example? What's the purpose?
So why do we have 4 routers here? Well, this is Switzerland. Perhaps this is in Lausanne. This is in Geneva. This is in Zurich, and this is in Lugano. So typically, you connect to other networks at different physical locations, which is the case for practically every network that is not ridiculously small.
So on top of the TCP layer network that we defined, we adapt the BGP. So
Yes. So here you have a network with 5 routers. And in this case here, the 4 routers that are at the border will implement BGP in order to discover the rest of the internet. And the 5 routers will implement their normal interior routing protocol. And the 2 will work together. It's a bit complicated, and that's, we will see that in detail in the coming hours, how the 2 work together. But in most cases, we need more than 1 BGP routers. That's why the thing is worth a lecture and is not completely trivial. So, a quick check. I am inside the domain D3, and I'm suggesting 3 possible BGP messages that can be sent. So for example, C could send to A the message with the path D3, D2, X, X being something outside, to prefix N1. And similarly, D could send this to E and C to E, which are the ones that may be sent. On ne peut pas cliquer. C'est pas dans le... Merci. It's better if you connect it. Five more seconds for your first BGP simulation. Aha. So the correct answer is number 4. So this route, D3, D2, X, N1, is in fact this, right? It has So somewhere at the top there is X that says I'm connected to N1. D2 repeats this to D3, and it has been learned by D, because it's D that's at the interface between D3 and D2. So when D gets that information, D, of course, will repeat it to E. That's part of the rule of the game of BGP. In principle, you repeat inside the domain all the information you've heard. So this will be in past. D will send that to all other 3 BGP routers inside the domain. Now about C. C has heard this information from D. But this is an external. Should it repeat to A? The answer is yes, because A is an external neighbor. So 1 will also take place. Now 3 will not take place, because C should not repeat to E this information, because E will have the same information firsthand directly from D. So those are the 2 messages that will take place. So although that is very simple and trivial, it's very important to understand how BGP works. So we see the mechanism. We simply repeat what we've heard in all directions. Except, of course, we avoid inside the mesh to repeat things unnecessarily. So D1, for example, we learned of another path to go to prefix N1. Of course, it has learned firsthand from X, so it might discard this information if it's not interesting. But this top information here, which is probably better for D1, might disappear one day. For example, the direct connection to X that exists here might be broken, in which case D1 would be happy to have the other information. Okay, let's continue. Is this closed? Yes. No, it's open. Five more seconds. And the correct answer is number 1. Of course, in the case like G to E, they are probably on link of each other, they're directly connected. But in a case like C to F, they are not directly connected, but they must implement a TCP connection. G and E will also implement a TCP connection over the direct link. Why a TCP connection? Why not use UDP? For retransmissions, yeah. It's to simplify. As we'll see, BGP is fairly heavy code, primarily because the number of prefixes that exist in the internet today is order of 500,000. So what I've illustrated here, like XN1, it's in fact a table with 500,000 entries. So you need to give that information, store it, go through it, process it, etc. So it's fairly heavy processing. So you use TCP. When you do heavy processing, you don't want to have to handle the case of a message being lost and repeat and keep a timer and everything. Last question. A is a stub. So a stub means it's a dead end of the internet. Once you've gone there, you can't go, you can transit through A to anywhere else. Could ASA avoid using BGP? And if so, how? Yes?
Does EPFL and switch communicate using BGP?
Haha. I'll answer that after the quiz. Okay, 5 more seconds. It is not graded, so. Well, the correct answer is 2 is correct. I'm not sure 3 is incorrect. There are certainly other methods to do, but 2 is certainly correct, and 3 perhaps also. What is wrong is number 1. It's not true that inter-domain routing requires an inter-domain routing protocol. It's not true. Okay? You require it if you want to do automatic configuration of it. Now, if your configuration is completely static from an inter-domain viewpoint, then you can put a static configuration into your system, which is what is done here. If we put A2 in this very simple case, A2 is the only interface of A to the rest of the world, which is bad from some viewpoint. If A2 crashes, you've lost your interface. But let's discuss that in a second. In this scenario, A2 is the only interface. So if you need to go anywhere, assume A is EPFL. If you need to go anywhere else than EPFL, what you need is to go to A2. And this can be reached by having A2 inject in RIP the prefix, the default route, which is 0/0. So A2 will do in RIP, I have a directly connected prefix, which is 0/0. And then all routers inside A will learn that their default route is the shortest path to A2 by the mechanism of any interior routing protocol. So by doing that, any packet that goes to A, so back to your question, does EPFL do this? Yes, A is EPFL, and D is switch. So this is exactly how it works, except at EPFL we have 2 routers to connect to switch, because if one fails, the other will take over. Here, if there would be only one, you can do this. Now, if you want to have a bit of reliability, how can you fix the problem of the single point of failure? So here we don't run BGP, right? Well, assume there is a direct link from A4 to some other router, hopefully not the same, because then we again have a single point of failure. Then A1 can do the same thing. A1 can inject into RIP 0/0. Right? So you will have 2 routers that say, I'm directly connected to 0/0. What will be the result of this inside my routing domain? Where will packets go to the outside? Yes? If you're closer to A1, you will go to A1. If you're closer to A2, you will go to A2. So we'll go to the closest of the 2 by shortest path routing. That's how it works. So if you want this to happen, then you do it. You give the 2 connections, and then traffic will go to the nearest of the 2, which in most cases is probably what you want. Now, if one is in backup, for example, if A1 is in backup and you want all traffic in principle to go to A2, because the link at A1 perhaps is more expensive, you can do the same thing, but give a larger weight to your direct connection. A1 could inject the default route 00, but instead of saying, and the cost from me to this is 1, I give a cost of 8, for example. Therefore, for most, if the network is not too large, with RIP, all traffic will go to A2. And if A2 crashes, then the other route will take over and traffic will go to A1. Voila, so take home message. Well, you can here statically configure the connection, the default route. Here it is static in the sense that it is injected into RIP at points where you know you have a default connection to the outside. It is static, but it's very minimal static configuration. So it's less in configuration than in BGP. So whenever you can do that, this is what people will do. This is why you have domains that don't have an AS number because they don't need to run BGP, which saves also a lot of cost on the routers because BGP requires very powerful routers with a lot of CPU and disk and everything. Voilà, that was our first approach to BGP. before we dive into how BGP routers work, we need to speak about policy routing, which is the very special thing of interdomain network. As I had mentioned, the interconnection in the internet is self-organized. So where does it occur? It can occur by having two networks agreeing on sharing a line. So for example, you use an optical fiber between a switch and the US, the equivalent of switch in the US. And then the cost of this fiber has to be paid by someone, so perhaps shared between Switch and CERN and the US. Or very often, you connect into interconnection points. So you may have heard of May West and May East in the US. Those are the two big American interconnection points. There are also two similar smaller interconnection points in Switzerland. Those are typically basements of a commercial building in which there are lots of very high performance switches and routers. And then anybody who wants to connect to the rest of the world can simply connect to these points, which is much more efficient. Now that's for the physical connection. Now the physical connection doesn't mean that any logical connection is okay. And in particular, so not in practice you can do whatever you want with tuning BGP is part of the business process of a given operator. But in practice, very often, the only important thing is to know who pays. So when you connect to someone else, you can be paying to that network for carrying your traffic. This is what EPFL does to Switch, or what Switch does probably to America, although those things are never made public. It's probably what Switch does to be able to connect to American research networks. So typically the small pay to connect to the big. Now when two big connect together, Sunrise and Swisscom, for example, in Switzerland, then they would tend to say we are peers. So I connect to you so that all my customers can access yours and vice versa. We are two big players, so there is value for both of us to be interconnected and to be interconnected with good quality. Therefore, we will do it on a non-for-profit basis. It's called shared cost peers. So we interconnect together. I don't pay anything to you, you don't pay anything to me, and we share the cost of the interconnection, which is perhaps renting a rack in interconnection point or leasing a line to go from me to you. Then there are similar cases where it is inside an organization. Inside an organization, in principle, we don't use BGP, except organizations tend to be very moving and fluctuating. For example, a part of EPFL is located in Neuchâtel, which a few years ago was not EPFL. So we have two pieces of networks that are in fact run as two separate networks. In a case like this, we might want to interconnect them via some form of BGP, which was done at the beginning, is no longer done today. It's called siblings in that case. But let's see an example, a very simple example, which is the very typical one. You will see a more contorted one in the lab, but the very typical example is this one. I have three ISPs. ISP 3 is American, ISP 2 is European, and ISP 1 is perhaps a multinational company, perhaps IBM, for example, which has, or Google, that has an international network. Then ISP 2 and ISP 3 will agree to share a transatlantic link because they want to serve their customers and be happy. And the links, typically the local links, are of course much cheaper than the transatlantic cable. So if you take the viewpoint of ISP 3 and it has some traffic to send to ISP 1, then it should send it locally. So if you send traffic to Google and you're in America, you will send it to a Google router that's in America. You will not first go to your European peer that would then connect to it. So this is typically what will happen. However, if you take the viewpoint of ISP 1, now Google probably is not happy, although we never know with Google, might not be happy to serve as a transit operator if there is some traffic going from US Print to Swisscom, then physically it is possible to route it via Google, via ISP1, because the connection exists. We could go this way. But ISP1 might not like to do this because it is not offering a transit service. ISP1 is not in the business of carrying traffic from an American ISP to a European ISP. It's not a transit ISP. Now, is it the case of Google? I don't know. For IBM, certainly would not like to do this. Now, Google, you never know. They might be happy to have all the traffic, to be able to read it and get all information. And they have probably the means to carry all the traffic. So that might be a different example. But assuming ISP1 does not want to do this, then this is exactly a policy routing case. The routing in BGP must be such that packet that goes from C3 to C2 should flow on the direct link ISP3 to ISP2 and never over the direct link ISP1. Even though ISP1 is connected to ISP3 and ISP2, and even though ISP3 might want to send the traffic to ISP1 because it finds it cheaper. Cheaper because the link across the Atlantic costs a lot, and typically you monitor the amount of traffic that flows on the link. If the link is full, then you need to put a bigger link that is more expensive. So if you can reduce the amount of traffic, you would like to do that. But ISP1 would not like to do it. That's exactly a policy conflict that might occur. How could that be implemented? Well, by typically what you will see in the lab in the name of import and export filters. So when a BGP router gets an advertisement from another peer, the BGP router might decide to keep it or not to keep it, depending on whether it likes it, depending on the policy. And similarly, when a BGP router knows of a route, it may decide to inform another router in a different domain or not. That is the export policy. So the combination of this might lead to what we want. For example, here at ISP1, ISP1 could put in place the following import filter. It would decide from C1, C1 is a customer of ISP1, I would accept everything that this guy says to me. From ISP2, I would expect everything, not everything that this guy says to me, but everything that has a prefix that is in C1. And similarly, from ISP2, I will accept everything that has AS path ISP2. And I would accept also ISP2 C2, which means I would accept all prefixes that are in ISP2, so the internal Swisscom prefixes, and the internal prefixes that are in C2, which is a customer of Swisscom. But I would not accept, if this is an exhaustive list, I would not accept an announcement done by ISP2 from someone who is in another domain. And similarly from ISP3. Now, if we look at the export rules, ISP1 similarly will announce to C1, who is a customer of C1, everything, because he wants to serve C1. But to ISP2, it will not announce the routes that have ISP3 in the path, for example. So ISP1 has accepted all the routes from those guys, but he will not send them back to ISP2. So ISP2 will not know that there is a path through ISP3 to ISP3 that goes via ISP1. And if ISP2 just runs BGP rather than trying to hack the internet, ISP2 will have no way to find out and therefore will not send traffic to C3 directly to ISP1. In particular, we see that ISP1 does not announce C1 to ISP2, and ISP1 refuses to import C2 from ISP3. Right? So C2, that is known to ISP3, but when ISP3, who knows of this customer here, wants to inform ISP1, ISP1 will not accept it because he's not a direct customer of ISP3. So this is an example of typical rules, but again, you can do whatever you want. And one of the difficulties of BGP is to make sure the filters you put in place are not buggy, that they are not against your policy. But typically, we see that a customer announces to a provider everything and accepts all routes, but between share peer costs, we announce or accept only the internal routes inside ourselves or inside our customers. Voila, this is how we can think of what BGP is doing. After we'll do a break now, and in 15 minutes we will start diving into how a BGP router does its job.